Welcome to emstatonline. Today we are going to see the application of eigenvalue problem in stretching of an elastic membrane. An elastic membrane in the x1 x2 plane with the boundary circle x1 squared plus x2 squared equal to 1 is stretched so that a point P of x comma x1 comma x2 goes over into the point Q of x1 comma x2 given by y equal to ax, where a is 3, 3 by 2, 3 by 2, 3. Find the principal direction, that is the direction of the position vector x of P, for which the direction of the position vector y in Q is the same or exactly opposite. What shape does the boundary circle take under this deformation? We are looking for vector x such that y since y equal to ax, this gives ax equal to lambda x. If y is equal to lambda x, y is equal to ax is given, so ax equal to lambda x. An eigenvalue problem in the component of ax equal to lambda x. So a minus lambda I into x equal to 0. So circular matrix. So determinant of a minus lambda I equal to 0. So we need to find out the characteristic equation of the given matrix. The matrix A equal to 3, 3 by 2, 3 by 2, 3. So A minus lambda I equal to 3 minus lambda, 3 by 2, 3 by 2, 3 minus lambda equal to 0. This is square 2 cross 2 matrix. So easily we can write the characteristic equation. So just second order degree, so lambda squared minus lambda into sum of leading diagonal of A plus determinant value of A. So lambda squared minus lambda into sum of the diagonal 3 plus 3 6 plus determinant 9 minus 9 by 4, that is 27 by 4, 6.75. So the characteristic equation is lambda squared minus 6 lambda plus 6.75, that equal to 0. So we need to find out the lambdas. Multiplication is 6.75, addition is minus 6. So this one we can write lambda minus 4.5 into lambda minus 1.5, that is equal to 0. So addition is minus 6, multiplication is 6.75. So lambda 1, lambda minus 4.5 equal to 0, lambda minus 1.5 equal to 0. So lambda 1 equal to 4.5, lambda 2 equal to 1.5. In solution, lambda 1 equal to 4.5 and lambda 2 equal to 1.5. These are the eigenvalues of the given problem. Now we need to find out the eigen vectors corresponding the eigenvalue 4.5 and 1.5. So 3 minus lambda 3 by 2, we can write 1.5. This 1.5, 3 minus lambda into x1 x2 equal to 0. First lambda 1 equal to 4.5. So 3 minus 4.5, 3 minus 4.5, 1.5, 1.5, 3 minus 4.5 into x1 x2 equal to 0. So this value is minus 1.5, 1.5, 1.5 minus 1.5, x1 x2 equal to 0. So minus 1.5 x1 plus 1.5 x2 equal to 0. The second equation 1.5 x1 minus 1.5 x2 equal to 0. So the two equations are same equations. We can write minus 1.5 x1 equal to minus 1.5 x2. So x1 equal to x2. Let us assume x1 equal to 1. We can write 1 comma 1. That is equal to x1 x2. Now we need to find the theta, because which angle it will stretch. Theta equal to tan inverse of x2 by x1. So theta equal to tan inverse of 1, that is equal to 45 degree. So the lambda 1 equal to 4.5 and the eigenvector is 1, 1 and theta is 45 degree. Let's find the second eigenvector 1.5. So 3 minus 1.5, here 1.5, 1.5, 3 minus 1.5 into x1 x2 equal to 0. So 1.5, 1.5, 1.5, 1.5 into x1 x2 equal to 0. So your equations are same equations, 1.5 x1 plus 1.5 x2, here 1.5 x1 plus 1.5 x2, that is equal to 0. So we can write x2 equal to minus x1. So assume x1 equal to 1, if x1 is equal to 1 means we can get 1 minus 1. So we need to find out the angles. Theta equal to tan inverse of minus 1 case, that is equal to minus tan inverse of 1, that is 180 minus tan inverse of 1. So 180 minus 45 degree, that is equal to 135 degree. So these vectors makes make 45 degree and 135 degree angles with the positive x1 direction. Positive x1 direction. They give the principal direction. The eigenvalue shows that the principal direction the membrane is stretched. By factors 4.5 and 1.5 respectively. According, if we choose the principal direction as a direction of new Cartesian coordinates as direction of new Cartesian u1 u2 coordinate systems with the positive u1 semi-axis in the first quadrant and the positive u2 semi-axis in the second quadrant of the system, and if we get u1 equal to r cos theta and u2 equal to r sin theta, then a boundary point of the unstretched circle membrane has coordinate cos theta and sin theta. Hence, after the stretch, we have Z1 equal to 4.5 cos theta, Z2 equal to 1.5 sin theta. Since cos square theta plus sin square theta equal to 1. This show that the deformed boundary is an ellipse, because z1 squared by 4.5 squared plus z2 squared by 1.5 squared equal to 1. The ellipse equation is z1 squared by 4.5 plus z2 squared by 1.5 the whole squared equal to 1, with principal semi-axis 4.5 and 1.5 in the principal direction. The graphical representation it's a unit circle x squared plus y squared is equal to 1. This angle 45 degree second one 135 degree, so 90 degree plus 45 degree, so 135 degree. So these are the principal directions. Here. But the ellipse semi-major axis 4.5, let us assume here semi-major axis 4.5 and minor axis 1.5. It's like ellipse. Similarly here just like ellipse. So the circle x squared plus y squared is equal to 1 is stretched, or the deformation boundary is an ellipse.